next lecture. Well, now I have the pleasure to introduce Professor Shoushan Zhang. He is going to talk about extensive shower arrays and the LHAASO observatory. So, please.
Okay, thank you. And it is very amazing school. I'm very glad being invited here. Okay, thank you for your invitation. So my name is Shoushan. I work on LHAASO experiment, and I'm from the Institute of High Energy Physics, Beijing, China. So now today my talk. My talk. Because the previous lecture have many introduced much on extension ISO array, so I will give very brief introduction to this part, and I will focus on the introduction of LHAASO experiment, including the result of gamma ray astronomy and also cosmic ray spectrum around the knee. Also, I will give you a few slides to introduce you about the progress of the LHAASO. Okay, I think all you know about the cosmic ray was discovered in 1912 by Hayes, and he also won the Nobel Prize in 1933 for his discovery of the cosmic ray. And so, as you know, the cosmic ray is a charged particle, so his direction is deflected by the galaxy magnetic field. So we cannot using the cosmic ray to point to direction to point to the source. But fortunately, cosmic ray interact with the ambient medium and produce the pi 0 and decay to pi to gamma, and we can using the gamma to point to the source. But we detect the gamma ray source, but we cannot say we found the cosmic ray source, because the gamma ray also can be produced by leptonic process. So this is also a difficult work to study. So now we have the gamma ray astronomy, also the neutrino astronomy. And it's extreme high energy cosmic ray astronomy. Okay, so okay. So here I want to say is about it, the cosmic ray spectrum follow the power law, and with index of minus 2.7. That means the flux of the cosmic ray decreases quickly with the energy. So if we want to be detect higher energy, you need a very, very big detector array. So from the direct measurement, we can put the detector on the by the satellite, also some balloon bomb experiment. We can direct measurement the cosmic ray. This cosmic ray we cannot build bigger detector. We can sometimes the detector area is about less than 1 square meter. So such kind of detector can measurement the cosmic ray below 100 TeV. It can identify the cosmic ray very element very well, but to reach the higher energy, we need the ground-based detector array. For the ground-based array, because the atmosphere, the cosmic ray first interact with the atmosphere, So they are produce the air shower. We only measurement the secondary particle. Different kind of the secondary particle, we design the different kind of detector. Something for positron, electron, or gamma, we are using the scintillator detector. And for the Shoushan light, we design the Shoushan telescope. And for the fluorescence, we design the fluorescence detector array. Yeah. Here I show you some extension of our experiment. This also can be introduced in the previous lecture yesterday or mostly in yesterday. Yeah. So here I don't want to talk more about it. And in the future, okay, in tomorrow, Ulyss has introduced you the SWGO, and also some people told you about the CTAO. Yeah. Also the next generation the neutrino telescope, ICTP-2. Also we here today I will introduce you the lighter. So this is the video about the one event of one shower. Okay, you can see here the particle reached to our detector array, and it was collected by the detector, and we know we measure his position and the arrival time. And then the shower front can be measurement well. And we using the shower, okay, using the shower front. And we have the shower front tangent plane. And this the shower direction is vertical to this plane. So we use this kind of method that we can reconstruct the shower direction. Okay. So here I want to say is that, so emphasize is here. For these two kind of shower, one is from the gamma and one is from the cosmic ray. You can see here, from the gamma induced the shower, there are no muon here. And for the cosmic ray induced the shower, you can see muon. Muon is from the charged pion. Yeah. So this is really important. The muon content can be is a key parameter for gamma pressure discrimination. So here I want to tell you is about the other really important parameter is the shower maximum. Shower makes different kind of particle. They have the different at the same energy. They have a different shower maximum. So as you can see here, in the middle of this figure, you can see the difference in shower maximum between the proton and the ion is about 120 gram per square centimeter. So, shower maximum is also a mass sensitive parameter. And then now, I introduce you the LHAASO experiment. Okay. I think most of you know about the LHAASO experiment. LHAASO experiment is located at the highest mountain, Sichuan, China. The altitude is about 4,410 meters. It is very convenient to access the LHAASO site. In the nearby the LHAASO site, they have the airport, Daoxiang Airport. The distance between the airport and the LHAASO site is about 10 kilometers. And the LHAASO 4 array began to begin operation in July 2021. So LHAASO collaboration now have about more than 300 members, covered 6 countries, and also the 32 institutions. We also signed the MOU with 8 international detector array. Okay. For example, neutrino telescope, chemistry net, interest, backward GVD, also the Cherenkov detector, such as magic, Veritas, and also LST of CTAO, yeah, in the North sky, in North Hemisphere. And also we have signed the MOU with the space-borne experimenter, Iloseta and Dampe. So, LHAASO experimenter has 4 kinds of detector array. In the center is the water Cherenkov detector array. The area is about 78,000 square meters, and surrounded by the scintillator detector array. It's covered area of about 1.3 square kilometer, and the muon detector array is covered area is about 1 square kilometer. Okay, also have the 18 Cherenkov telescope. Okay, his physics topics include gamma ray astronomy, charged particle, cosmic ray measurement, also new physics research. And here you can see here, this Earth bag is the muon detector, and the water tank is buried under the ground. Above the water tank is the 2.5 meter soil, thick soil. And this can be used to absorb the electron, positron, and also gamma. Only muon can pass through. So this is called a muon detector. And also you are using a scintillator to detect the electron positron. Above the scintillator, we have a lead to convert the gamma into the electron positron. Okay. And here this table I show you to compare the LHAASO with other experiment. LHAASO now is the from the a few TeV to a few several hundred PeV. In this energy range, LHAASO is the biggest detector array. Scintillator array is the biggest. Also, the muon scintillator area is the largest in the world. Okay. Okay, here I show you 2 events. One event is the cosmic ray event, and the other event is the gamma ray event from the CLAF. This event is the energy is around 1 PeV. You can see here, this circle means the muon. You can see here for cosmic ray have many muon here. You can see many circles here. And from gamma-like event, you can see real really little muon. Yeah. This is the real event measured by LHAASO. And so muon is very powerful for gamma and has long discrimination parameter. So we can use this information to select the gamma ray out of the cosmic ray. You can see here about one we can suppress the cosmic background 1 in 10,000 at around 100 TeV. Yeah, so it's almost the background fully. Yeah, so we can select at least 90% of gamma ray. Here I show you the water triangle detector array. Okay, they have three pools, three big pools, and each pool we also divide into small cells. The unit size is about 5 meter by 5 meter, and in each unit the water is about 4.4 depths. And each unit we have using the 2 PMT, one big PMT and one small PMT. For these two pools, we are pool 3 and pool 2. We are using 20-inch PMT plus 3-inch PMT, and this one pool where you are using 8-inch PMT plus the 1.5-inch PMT. This pool can cover a little higher, cover energy to 10 PeV. Okay, but these 2 PMT because use the bigger PMT, so the energy threshold will be lower to 100 GeV. Okay, here I just show you the a photo inside of the one pool. Here show you this is the 20-inch PMT. This is the 3-inch PMT. And here show you really big commercial event. I don't know which energy it is, but it has trigger maybe one or 2 PeV maybe. It's trigger the three pool. And for LHAASO triangle telescope, it's only designed for the cosmic ray measurement, not for gamma ray. So the diameter of the mirror is about 2.3 meters. And here we are using the CLAF camera. And if we using the CLAF, so we can so telescope can be operated in the moonlight, even in the full moonlight. This is really important because it can increase the duty cycle for such kind of telescope. Here what I want to show you. Here is the telescope run in the full moonlight. Okay, you can see that you can see triangle emission can be measured well, and even trigger rate, yeah, is always stable. But here I will point out later in the full moonlight, the energy threshold of telescope will be something like above 100 TeV because of the background light. Yeah. Also, if the moon in the field of view of the telescope, it's the moonlight is too strong, so the telescope was saturated. So in this period of time, the data cannot be used. You can see here now the trigger event almost 0. Yeah. Okay, for the calibration, we have we are using 2 ways to calibration our triangle telescope. One, we put LED here to calibrate the Singapore camera every day. And we also, in LHAASO site, we also have about 4 lasers used to calibrate the end-to-end calibration our triangle telescope. Also monitor the atmosphere in LHAASO site. Where I say the end-to-end because the laser is emitted to the sky, and then the light transfer to the cylindrical telescope is cover light absorbed in the atmosphere or in the air. Also mirror reflectivity and also the response of the camera. So this we put this total together. Effect together. So the telescope will be calibrated by this measurement is we call it end-to-end calibration. And here I show you the LHAASO sensitivity curve. I think this figure has been shown many times. This red line is the LHAASO sensitivity curve. LHAASO sensitivity curve, around at about 10 TeV, maybe for 30 TeV, about 30 TeV. Yeah, it's the sensitivity is higher than current detector array, even higher than the CTA or CTA. Here, oh, sorry, here is 1 year. Yeah, I mentioned that here is 1 year sensitivity. CTA is the 50 hours. Okay. So also LHAASO sensitivity is also higher than HAAC at a lower energy. Okay. We are also using half array. About 1 year's data, we have discovered 12 pevatron in our galaxy. You can see here those this source, the spectrum, photon spectrum. You can see here. You can see no clear cut off here, at around 100 TeV. That means if we can using more data, we have the energy can be reached to something like 1 PeV. Yeah, so this is the first time so many pevatron will be discovered in our galaxy. So LHAASO started a new era of the ultra high energy gamma ray astronomy. And we are using more data. 2 years for array data. We discovered more gamma ray source. We in the 2024, LHAASO released the first catalog. In this catalog, have the total source is 19, including the very high energy and ultra high energy gamma ray source. And the ultra high energy gamma ray source is increased to 43. Okay. Those sources you can see here associated to the pulse wind nebula, supernova remnant, and also the massive star cluster and so on. And here is really interesting is that most of the source is associated with the PWN. This is really interesting. Yeah. So we have so many pevatron in measured by LHAASO, so we can study this source more detail. First, really famous PWN is the CLAF. Yeah, we can see here the energy spectrum is measured by LHAASO, cover the 3.5 decade of energy, and the higher energy is reached to the 1.1 PeV in the science paper. Yeah. But the highest photon energy now is the 1.4 PeV. if the CLAF photon energy spectrum is come from the lepton. That means we require the electron energy should reach to the 20.8 PeV for to produce the 1.4 PeV gamma. This for the higher energy electron, it lost its energy very quickly in the magnetic field. So this means we require about 26% acceleration rate. It's about 1,000 times higher than SNR trigger waves. This is really challenge the model. Yeah. But also, some people also can be say this may be such kind high gamma ray maybe come from the hadron process. But we can't say is have clear conclude that this photon is come from which process is from lepton or from hadron. We need more data, at higher energy. Yeah, we need more data. I think maybe in a few years we can get a clear conclusion. So here I show you another PWN. Okay, J1849. This source we have measurement the highest energy, and now it's reached to the 2 PeV. That means we require the maximum electron energy is about 3.7 PeV to produce the 2 PeV gamma ray. Okay, this also challenge the model. Okay, now I will introduce you the supernova remnant. Okay, LHAASO has detected many supernova remnant. So I will give you some example to show you. First, the KSA. KSA is about 350 years old. It is a young SNR. And from the hay, something like haze, or also the here can see Fermi and Veritas, and also from their measurement the energy below the 10 TeV. Also LHAASO to detect we can know about the 10 TeV we don't see any photons. Yes, it's well. Sorry. It's right. Oh yeah, yeah, right. So we don't see any photons above the 10 TeV. This is some people, many scientists before think the SNR may be the pivotron. They can produce the they can accelerate the cosmic ray up to the near region, cosmic ray near region. But for this young SNR, we don't see the energy higher than 10 TeV. And also we can measurement another SNR W51C. This is the middle age SNR. This SNR, the higher energy we can see here is about reach to the 300 TeV. And also in here you can see the above E-cut is about the 60 TeV. Yes, this is the pivotron, maybe the pivotron. But the energy is not enough to reach to the need region. Yeah, we need at least the 1 PeV gamma to reach the PeV region. The common need region. Okay, here I show you another middle age SNR, IC443. Yeah, this also have the higher energy is it's about how much? Okay, it's about several hundred TeV, and you can see here yeah, we can see here that this is two regions. There are these two components. One is the point source, and the other is extended source. You can see this is the point source and spectrum. This is the extended component spectrum. And the LHAASO is extend the 20 the energy to 20 TeV. When we say why the gamma ray is produced by the cosmic ray, not from the laboratory, we need one evidence is we should see our gamma ray is correlated with the nebula molecular cloud or not. Here you can see here is the molecular cloud, and also the color is the gamma ray. So you can read something like they are correlated each other. So we may think the SNR, this just kind of SNR may be produced. The gamma ray may be come from the Hadron process. Okay. In our galaxy, we about 20 young massive star cluster in our galaxy, and dozens of is the OB and the WR stars. And also, LHAASO have detected such a young massive star can produce can emit the ultra high energy photons. For example, here I show you the Sigma bubble. Yeah, this is a really powerful region, and this we for the LHAASO we found this region is maybe the can produce the cosmic ray up to the PeV. W10 PeV energy range. Here I show you here the energy above the 1 PeV, about 8 gamma rays, 8 event gamma rays above 1 PeV was detected by LHAASO. And here you can show you the morphology here. Okay, yeah. Sometimes you can see here this event is more related to the Cygnus OB2, and the highest photon energy is reached to the 2.5 PeV. Okay, here this table show you the detail of this 8 event. And again, we say that this signal ratio is the cosmic ray source. We also need to track the cosmic ray is correlated with the gas or not. Here you can see the contour is the gas distribution, and the color is the gamma ray. Okay, you can see they are, at least for the figure, you can see they are correlated each other. Yeah, you can see. And here we also, maybe the cosmic ray may be produced by the, maybe come from the diffuse gamma ray. Okay. we expected it. Here line is the diffuse gamma ray, and this dot is the our data. Yeah, is the gamma ray is about 2 times higher than the diffuse gamma ray. So that means the gamma is come from the source, not from the background. Okay, W43 is a galactic mini star starburst. This here is W43. It is located at the expected transition zone between the bar-dominated region and the normal galactic disk. This region contributes about 10% of the galactic star hormone rate. And in this region, it's rich in HI gas. So it's really interesting. If we detect the gamma ray from this region, okay. So this is the inclusion. We also have detected the spectrum up to 400 TeV, and the cutoff is about 30 TeV. Okay, and you can see here the gamma ray emission shows a good relation with the dense gas. So W43 it is a candidate of the hadronic source. It maybe can produce the cosmoless up to PeV energy. Now I will introduce some source from the macro quasar. Macro quasar is the binary system. In the center is the black hole, small black hole, and the companion is something like a star, and the black hole get the energy from the ambient the star, and then at some condition, the result will be happened, and the particle will be accelerated. So maybe we can get to the photon energy higher than 100 TeV. So and before the LHAASO experiment, no one have expected the macro quasar will be produced the gamma ray above the 100 TeV. But now in LHAASO we have detected we have found 5 out of the 12 macro quasar in LHAASO field of view, and we found that the gamma ray energy can be reached to above the 100 TeV. Okay, this is here I list the name of these 5 gamma ray, the macro quasar. And here show you the macro quasar SS433. Okay. Okay, this is 433. Okay, let me show you the next. Okay, for macro quasar. And the last and the measurement energy. Okay, the energy is reached to something like 200 300 TeV. And you can see the significance above the 100 TeV is reached to the more than 5 sigma. Okay. And also, this gamma ray is correlated with the SI cloud. So the macro quasar is very powerful source, can produce the gamma rays reach to the PeV, even 10 PeV, something like that. And here I show you the other 4 macro quasar, V46, 41, and so on. Okay, and then you can see the spectrum for at least for macro quasar, and the energy of the highest energy of the photon can be reached to about 1 PeV. Yeah. So that means 1 PeV gamma, something like can be come from the PP collection. The energy of the cosmic ray may be 5 times or 10 times of the gamma ray. So 1 PeV means something like 5 PeV, 10 PeV gamma ray, the cosmic ray. So so that means the macro quasar can produce the cosmic rays around the knee region. The knee of the, as you know, the knee of the cosmic rays around the 3 PeV. So here I would like to introduce you the diffuse gamma ray. This red dot is the LHAASO measurement result, and this is expected. What we expect the diffuse gamma ray? What means it is expected? Expected means we are using the local cosmic ray. Local cosmic ray is measurement in our on the Earth. Energy spectrum, something from the proton or particle spectrum, we know the flux of the cosmic ray, and also we know the gas distribution in our galaxy, and then also taking account the cross section between the PP interaction, so we can calculate the expectation diffuse gamma ray. But for now, you can see here the LHAASO data is about 2.7 higher than the expectation flux. So in LHAASO experiment we also have learned recently we have measured the proton spectrum. I will introduce you later, and we also use the new result to calculate again the expectation. The LHAASO data is also below 100 TeV. Is also higher than the expectation, but above 100 TeV, something like it can be missed other. This may be come from when we measurement the diffuse gamma ray, we needed to subtract the point source, gamma ray source. Okay, but sun source is too weak. We don't. They cannot be detected. They don't be detected by our detector because our detector sensitivity is limited. So we don't know how to separate it. So this source may be contributed to while our data is higher than expectation. So here again, I show you the both gamma ray. This is I think this is the third time. Show you here. This both gamma ray. Some people have calculated the possibility is about once per 1,000 years. That means if the next such bright gamma ray will it happened 1,000 years later, and now you see for the AI now, maybe in the future, maybe such kind, maybe no human here at a later day. Okay, so it's really interesting both gamma ray. And here I saw how bright it is. I will show you here. I want to compare the gamma ray with the CLAF, because many of us know the CLAF very well. So here you can see here the gamma ray, the light of the photon from the gamma ray. This both gamma ray is in 270 seconds. We collect the 64 kilo photons, and you can see it's equal to 500 days CLAF. The real signals almost the same. Yeah, this is give you the idea how bright the both gamma ray is. And also for this both gamma ray, LHAASO have detected the highest photon reached to the 13 TeV. This is the highest energy of photon have ever measurement for the gamma ray. So this is very useful for study something like to control the EBLO, also to study the Lorentz invariant variation, also dark matter. Yeah, some people to use this source to study something like this lost topic. Okay, now I will give you introduce you the cosmic ray spectrum around the knee. Last year, LHAASO had published a particle energy spectrum around the knee from the 300 TeV to 30 TeV. And you can see here the knee, the cosmic particle knee is around about 3.7 PeV, and here you can see the composition change around the knee, light dominant below the knee, and the heavy dominant above the knee. Yeah, this is very interesting. And even we also need to select the single element component from our particle. How in the previous detector array, it's very difficult to do that. But now, LHAASO have the very powered muon information. Also, I have introduced you in the previous slide. Let's say that using the Schur maximum. Okay, so maximum can be we can use in Trillion Golf to measure the Schur maximum. This parameter. This parameter means the direction of the shower and the centroid of the image and this angle distance. This is related to the shower maximum. So here the proton. The pure proton is selected by using these two combined to mass center parameter. And we get about purity is about 90%, around 1 PeV. And we have the selection efficiency is 25%. And here, so the energy recursion, you can see here in the cosmic ray induced shower. They have two components. One is induced by the neutral pion, pi 0. You can see this is the electromagnetic component. And also this here is the H1 component for the pion, charge pion. And the charge pion decay to the muon. So we can use the muon information. And also Cherenkov light, we put this information together. We can get very well energy measurement reconstruction. We have very little system bias, less than 2%. Also around 1 PeV, we have the energy resolution about 10%. And also we have the proton spectrum. Here we can see here, the knee is around 3 PeV. And in here, we can see here the hardening is happening here. Yeah, the index is changed about 0.2. Yeah. And this is the first time, yeah, we LHAASO have the ability to get the pure proton. By even the select method, like the local measurement. Yeah. So here I show you here these are our particle and this is the proton. Here you can see knee of the particle is here and this knee of the proton is here. You can see maybe the particle need is mainly contributed by the proton need. So we are using the particle spectrum, separate the proton spectrum. You can see here the need disappeared. The particle the need disappeared. Yeah. So that means the shape of the particle need is mainly dominated by the is mainly determined by the proton need. Yeah, it's also really interesting. Also, you can see here the helium need. After you the particle, suppose the proton spectrum, the helium need. You can see here the hint of the helium need. Yeah, here. So we have the broader spectrum of proton from the IMS, DAMPE, and the LHAASO. As you know, the SNR can be reached the energy, something like reach to the 1 PeV, but for about 1 PeV, the cosmic ray may come from the competitive object, something like macro quasar, as I introduced you before. Okay, but we need more detail, take more effort to investigate such kind of topic. People now is working really hard on this topic. So here I show you the energy scale determine. Some people may interesting about how to calibrate the absolute calibrate the ground-based detector. We don't have the beam. Something like from the sun, you have a selector, so we can produce the proton beam to calibrate the detector. But for the ground-based detector, we don't have such kind of beam. But we can use the moon shadow. Moon shadow, moon can block the cosmic ray. If no geometric field, the moon shadow is at here. But such particle will be deflected in the geometric field, so the moon shadow will shift. So if we know the shift angle and we know the particle, so we can use this to and then we know the energy. Okay. So here you can see here with the moon shift. Moon shadow shift, yeah, it's measurement by LHAASO. I show you in this table. Okay, from the we also if we also from the below the 100 TeV, the most of the component is the lead component, proton and helium. So we are also know the composition well. So we can use that kind of method to calibrate the ground-based detector. At the moment, we have using 1 year, we get an uncertainty about 30%. Yeah, but we using more data, but something like 4 years data, we will be reached to the 10. The uncertainty will be reached to the 10%, and the data analysis is ongoing. Okay, now here I give you a little summary of the LHAASO. Here I show you LHAASO full array has been stably operating since 2021, and LHAASO has opened up a new ultra energy gamma astronomy era. With we have many new discoveries. Something like we have detected dozens of pelotrons. This is really useful for us to study the origin of the cosmic rays. And we also have detected both the gamma ray. And also we also have the measurement really precisely the diffuse gamma ray from 1 TeV to 1 PeV. At the moment, we found our data of the diffuse gamma ray is higher than higher than expectation. Okay. So LHAASO experiment also measurement the energy spectrum of a particle and the proton spectrum around the knee. Okay, and so in the future, with the more use new tool, something like AI, something we are using not like improve our analysis method, also using more data, we can get a more interesting result, and the more new phenomenon will be revealed. So we are waiting for it. And now here I would like to introduce you LHAASO. LHAASO is a large array astronomical telescope, and we plan to build 32 telescopes built on LHAASO site. And this table shows you a few parameters of the LHAASO. You can see in for a single telescope, the mirror diameter is about 6 meter, and the field of view is about 8 degrees. And for the camera, the number of pixels is 1,616. And we are mainly focused on energy range is from 1 TeV to 1 PeV. Yeah. As you know, for the ground-based detector, such like LHAASO experiment, it has a large field of view. It can be reached to about 100 degrees, but the angular resolution is not good enough. It's about 0.2 degrees. For the AACT astronomical telescope, yeah, it's good at the angular resolution. But the current astronomical telescope, their sensitivity is not enough to measurement the photon energy higher than 100 TeV. So we need new generation IHT, for example, CTA, also LHAASO. So we this is the one source measured by LHAASO. If you don't have enough angular resolution, it is possible for us to identify these two sources. So we need to reach to something like angular resolution reach to 0.05 degrees. We can identify it. Oh, okay. This source, gamma ray source, have two kind of source. One is the supernova range, the other is pulse wind nebula. Okay. You have the better angulation. You can measurement the morphology. Yeah, these results are from the measured by HEAS. Yeah, you can see here. Yeah. So this is really if we can measurement such we get lots information. This is really important to study the cosmic ray, the mechanisms. Yeah. So we put LHAASO, we put the LHAASO into LHAASO site. We also can use the LHAASO muon detector array. Yeah, as you know, the LHAASO muon detector array can provide very excellent gamma P discrimination. Yeah. Now LHAASO now is founded this year, and we now start construction. And we expect first telescope will be finished in this year, and 32 telescope full array is planned to complete it in 2028. So for the muon put a large chemical detector on the LHAASO site. We have the muon detector already. We also have LHAASO site also provide infrastructure. Yeah, that means you can see here we have the power supply, network, computing, data center, etc. So we don't need to build such infrastructure again. So we can put all our money to build the telescope. So this will save our money. Okay. And in the LHAASO site, we also can the observer time is about we can get about 1,400 hours per year. Yeah, this is also one good site for the Cherenkov detector. Yeah, although they have the rainy season from the June to September each year. Yeah, it is about 4 months. Sometimes it's almost the rainy or cloudy day. Telescope sometimes can be operated, but we even this month the Cherenkov cannot work, but we have at months we also can get the 1,400 hours duty observer time. And here I show you the muon. Here you can see here, if you are using the muon information, we can increase the sensitivity of LACTA by 1.6 times. Okay, yeah, especially for the essential source. You can see here, this is the this solid line is without muon information, and this dashed line we are consider about using muon, yeah, information. And here we are place the telescope between in the gap between the muon detector. As I introduced before, the spacing of the muon detector is about 30 meters, and our Cherenkov telescope is 6 meters. So they have enough space to put the Cherenkov telescope. Okay, we have here 4 in group, and we have 8 group. So now total is 32 telescope. And also Cherenkov, we can have 2 observatory model at least now. One is we can observe in the small zenith angle. We are using the total 32 telescope to enter the sensors. We can get the angular resolution is about less than, yeah, I think it's less than 0.04 degree, and above 10 TeV. And we also have the collection area is reached to the above the 1 square kilometer. And then the energy threshold here can be reached to the 200 GeV. Yeah, it's for this observation mode. And okay, here. And then we also don't need 30 telescope observation at sensors. We also can using the edge telescope. Also, is enough if we are measurement we follow large zenith angle. This large angle means the zenith angle range is from the 50 degree to 70 degree. Yeah. And we also can using this at telescope. We also can get the angular resolution above 100 TeV. Yeah, it's something like around 0.05 degree. And we can get a larger area collected area reach to the 3 square kilometer. Okay. And for the for the large genesis angle, the threshold will a little higher than the small genesis angle. Here is we can get at least from 1 TeV. Yeah. That's the threshold of the energy of the telescope of the detector array, telescope array. And here I show you, really interesting I show here is that we can, using the LHAASO, we also can see sun source from the galactic center. We still have something like 37 hours, in each year. Yeah, this is really interesting. We can, in the future, if LHAASO finish it, we can see the galactic center. Also here I list how many hours. Maybe I lost something to introduce the sensitivity here. Sorry. Okay. Here I show you the sensitivity of LHAASO. This is red curve is 50 hours, and this is the blue line is the sensitivity of LHAASO, 500 hours. You can see here, using the 50 hours, the sensitivity is above the 10, 20, 30 TeV. The sensitivity is lower than LHAASO, so we need more hours to get the reach to the around something like 100 TeV to let the sensitivity of LHAASO equal to the LHAASO. So this we mean the deeper observation mode. So here I will show you here why we show you here the table. I want to see in the I list here the top light, top bright the source in the LHAASO catalog. You can see here most of the source in each year have more than 500 hours in the light field of view. Oh, okay. So I think for the telescope, triangle telescope, almost it's the same as with the CTA magic haze. Yeah, you have the mirror, a camera, auto rotation system. Yeah, so I want to introduce you more detail to you here. So here I show you a photo of the prototype of a light telescope. Now it's in LHAASO site. Now we have the mirror and the telescope, but at the moment we don't have the camera. I think the camera will be in October. That means 2 months later we have the camera here, and we will start the operation of this prototype. Here I show you the light construction plan. Okay, this as I said, in this year August we have the first telescope will start coming training, and about in the second telescope will be finished next year. Before the May, of next year, and then the total at this time, 2027 February, we have the telescope here. Yeah, I say that if we have a telescope, we can get some exciting result. If we are into the large series angle, we can measure the sun source from something like galactic center, also from source really interesting, but macro quasar SS433, something like that. Okay. Also, okay. Okay, and now the full array of the, I said before, yeah, the total 30 telescope will be finished construction in 2028. Okay, that's all. Okay, thank you, everyone.
Thank you very much. We are open to questions on LHAASO or any other facilities described in the talk. Yes, Ulises, please.
Thanks, Shoushan. If you go back to slide 21.
21, okay. Oh. Okay. Twenty-one.
Yes, this
This
one.
one,
So
this
you,
one, okay.
you see, there is something that I mentioned yesterday in my talk. You have the fill factor of the muon sensitive detectors, yes? And the last column layer, coverage.
Coverage, yeah.
Yes, so, and this is the reason why probably, for example, Casamia, Jim Cronin did not detect the pevatrons in the 90s. They were too sparse. So you really need something like what you have. You have 4%, yes, of coverage in the for muons.
Yeah.
And this is really necessary. It's just to show, just to highlight that thing. Yes.
Okay, okay, thank you.
Okay. Any other question? Yeah, please, just 1 second.
Thank you for the talk. So I was just wondering, okay, very nice results from the observatory, but what have you learned and what would you make different if you were to build again the LHAASO? Is there anything else that you would change to make it better? Did you commit any mistakes or anything that you could do different now?
Different and what better data analysis or better result?
Yeah, if you have infinite money, how would you build another LHAASO?
Oh, I think if we have enough money, sometimes we maybe build large, but at least something like 4 times, 10 times. Yeah, you can get a more exciting result. The other choice, you maybe move to the southern hemisphere. Yeah, something like SWGO. Yeah. So if in the northern hemisphere, you need to build really big. Yeah, because now at current LHAASO is scientific enough. Yeah.
In LACT, you will have 32 telescopes.
Yeah.
And also you have the muon detectors. And what is the building in the middle? Yeah, I saw in the images that there is a building in the middle of the array. Well, what is that?
Building.
Building. Yes,
Oh,
structure,
oh, okay.
some structure. Perhaps you mentioned, but I didn't.
You mean here this one?
No.
Oh, WCDA. Oh.
No, but not in LHAASO. I mean in the array for the Cherenkov telescope, the atmospheric telescopes, the LACT. Yes.
Building.
No,
Okay, let me see.
Go up. Black. More. Yeah, the previous one. Yes. You see, you have 32 atmospheric Cherenkov telescope. You have the muon detectors, but what is the building in the middle?
This
Yes.
one.
Yes.
Oh, this is the water Cherenkov detector array.
Ah, okay.
Like Hawk.
Yeah, it's like Hawk, so it's water detector.
Yeah, water. Yeah. It's WCDA. This is the. So
Yes,
what
but
do you?
in one of the previous pictures,
What?
please go back.
Go back.
No, more, please. More. The other way around, but backwards.
Back.
Okay. Yes, that one.
This one. Okay.
Yes. So I was confused because I saw the image in front of the LHAASO, so I thought it was separate. But yes, okay.
Before.
I mix time with space. Sorry, my mistake.
Okay.
Well, yes.
Thank you for your lecture. Could you show again the sensitivity curve for LHAASO?
LHAASO. Okay. Okay. I think. Okay.
Looking at the 1 year sensitivity, we have a sort of inflection point at discontinuity at about 11 TeV. What's the reason for this?
This is here. You mean here?
Yes.
Oh, this from this curve from here is from the water triangle detector WCDA, and from this point is the from here to here is the chemistry. Yeah, genetic detector and the plus muon detector. Yeah, this is connected to each other. So the sensitivity sometimes like changed, different. Yeah, this is the reason.
You have another sensitivity graph at the end of your presentation when you show the LCTA together. Why do you not show all of this together? The LCTA and the last 1 year, for example.
Okay, let me see here.
Why did you separate these two things?
I separate. Oh, let me see. I separate. You mean here?
Yes. The blue or the red one, for example, and the purple one.
Yeah. What do you mean? It means this is LHAASO. This one is LHAASO. Can you see?
Yes.
Oh, you mean the LHAASO and the LACTA together?
Yes.
Oh, yeah,
It's
good suggestion. But the reason is one reason is that at the moment we don't consider is that the angular resolution, the LHAASO is 0.2 degree, but LHAASO LACTA have better angular resolution. So if we put together, the angular resolution will be something different. So you cannot put a simple put a letter together. But in the future, we can combine the data analysis, something using muon in genetic detector to improve the angular resolution, also the sensitivity. Yeah, this is analysis undergoing. We can optimize it, such a kind of data analysis method. Yeah. Okay. Thank you,
Okay, thank you.
Yeah.
Okay, we have time for 1 or 2 more questions. Someone? Okay. If not, let's thank Shoushan again.
Okay, thank you.
Lunch time now.